All right, as we shift to chapter 4, we're shifting our types of equations we're looking at. Back in chapter 3, we were looking at polynomial and rational functions, mostly polynomials, and then we had that last section about rationals. Here we're starting to talk about exponential functions. And in this section in particular, we'll be looking at their applications. We'll continue with one other type of function as we continue through chapter 4, which I can't remember if we encounter it in 4.2 or 4.3, but we will get there. Just a reminder, review, if you will, of what exponential means. Exponential means we have exponents. So this is an example of a few types of exponential expressions. If you have 3 to the negative 2, this is just a reminder, a negative exponent means that the value goes into the denominator. So it would be in the denominator as 3 to the positive 2. And of course, 1 over 3 squared would be 1/9. If you have a power of 0 means that you end up getting the value of 1. This negative, however, is not raised to the power of 0. If it were, it would have been written like this, -4 in parentheses to the power of 0. So what we really have here is this just the 4 that's raised to the 0 power. So the negative is still in front, but 4 to the 0, as I mentioned, is 1. So this one's actually -1. If you actually have a fraction that's raised to a negative, not just a single number like on the first one, we flip the fraction upside down completely. So the 2/3 becomes 3/2. And then the exponent will become positive when we do that flip. And then we would apply the exponent individually to the top and to the bottom. So 3 to the 4 and 2 to the 4. 3 to the 4 is 81, and 2 to the 4th is 16. And if you can't do that in your head right away, that's totally fine. Grab a calculator. It doesn't bother me in the slightest. You'd have 81 over 16. You might look at that and say, well, does 81 over 16 simplify? The answer is no, and even without trying, I know that the answer is no because the factored form that we had earlier was 3 to the 4th and 2 to the 4th, and 3 and 2 don't have anything in common. So when I multiply a bunch of 3's together, a bunch of 2's together, they're still never going to have anything in common. Okay, so that's just kind of a real quick review of some exponential stuff we saw happen back in chapter P. Specifically in this section, we're looking at exponential functions, which means a base, a, raised to a power, x. A few features about that. Notice that the base has to have a positive number. So when I mentioned before, taking like -4 to the power of 0, that's not an exponential function. Okay, that's not what we're looking at in this section. We're only looking at bases that are positive. And then also, we cannot have the base equal to 1. Imagine what would happen if you did. If you have 1 to a power, what happens when you raise 1 to any power? You get 1. Right? It doesn't change, and so it's constantly a 1, which makes it a horizontal line. So that's why it's excluded from the ability to be talked about like this too. So we aren't going to do those either. Now, in particular, it's not like somebody's going to throw those at you and say, is this an exponential function? I just want you to be aware those are the kinds of numbers you're going to see as positive numbers that are not 1. A few things about this. The domain, the x values for this are actually -infinity to infinity. You can put anything that you'd like inside here for x. Positives, negatives, fractions, decimals, zeros, everything's good to go. Okay, again, we're still working in the real number system, so we're not talking about imaginary things at all. But any of your real numbers are good to go. However, if you take a positive number and you raise it to any power, it always gives you a positive answer. So what that means is that my range is actually, I didn't write that right, I'm sorry, 0 to infinity. I always get positive numbers out when I raise things to powers. And it doesn't even matter if the powers are whole numbers or negative numbers, I still get positive values out of them. Okay, notice all of my examples on 1, 2, and 3 were positive, with the exception of number 2. And the reason it wasn't is because there was a negative being multiplied after I did the exponential part. Otherwise, always positive. Okay, so a couple basic graphs. There's 2 possible graphs that can occur. They're related, obviously, but they are different. They're based upon whether or not your base is a number bigger than 1 or between 0 and 1. If your base is bigger than 1, then well, actually, let me talk about what they have in common first. Both of them cross the y-axis at 1. Okay, so we're going to plot a y-intercept of 1. But if your base is actually bigger than 1, then you have an increasing function, which means it looks like this, roughly speaking. And if your base is a fraction between 0 and 1, then you actually have a decreasing function, and it looks something like this. Okay, so notice what we talked about. The domain, negative infinity to infinity on both of them. I can go as far as I want to the left, far as I want to the right. There's no asymptotes in there at all. The range is all above the y-axis. I'm sorry, above the x-axis. Y is greater than 0, right? Everything is elevated above in both graphs. So it fits in with what we already talked about over here for domain and range. I mentioned the y-intercept is the same for both of these. The y-intercept is x equals 0, y equal 1, so the ordered pair 0, 1. And you might also notice on these that we actually have a horizontal asymptote. Because of the sort of left-hand side of this over here, tapering off at the at the x-axis at y equals 0, we have an asymptote that's acting upon our graph. Remember, an asymptote's a line that you get close to and you don't touch. That's exactly what's happening on the left-hand side of that first graph. And equivalently, it happens on the right-hand side of the second graph. So I have horizontal asymptotes here. And again, remember, those are not 0. They are y equals 0. They're equations of lines. So I always have a horizontal asymptote at y equals 0 and y-intercept at 0, 1 for the basic ones. Now, we had a section in Chapter 2 where we talked about translating functions. Do you guys remember that? It was one you did with a video while I was gone. You shifted things up and down and left and right, and you flipped them over axes and things like that. Nod your head if you're kind of recalling what I'm talking about. Okay. So we can do that with these functions too, right? We can flip them down. We can flip them over the axis. We can shift them up and left and down and right and all that good stuff. It's based upon other features of the graph. So here on number 4, we see that happening, right? I actually have a +1 on the end, and I have a negative x in the exponent instead. And the question is, what happens when those operations, those features are present? How does my graph change? So we're going to actually talk about it from that same perspective when we did transformations before. We'll start with the one that I think is probably a little bit easier to determine. Do you remember what happens if you add 1 on the outside or to the end of your equation? How does that change a graph? Okay, but how does it shift the whole graph? Okay, so that's a possibility. Does it move to the right? It's either left, right, up, or down. It's definitely a translation. It's either up or left. So which one is it? We've got 3 possibilities now, left and right, up. Nobody said down. It's not down, so don't say down. It is up. This is actually a shift up 1. So let's talk about why. So if you remember, when we add something to the end or outside of the x value, it shifts it up or down. If it's a positive, it shifts it up. If it's a negative, it shifts it down. If we had added something in here, it would shift it left or right. Okay? Positive would shift it left. Negative shifts it right. It's backwards when you think about it from the inside perspective. Okay, we don't have addition on the inside, so we don't have any shifting right and left going on. However, we do have a negative. Negatives are all about reflections. When you take a negative and you put it either like this in front of the x or in front of the 3, it shifts things, it reflects things. It either reflects it down, in this case of what we're doing, right, over the x-axis, or to reflect it around the y-axis. Which way is it in each location? Specifically, the one that we're looking at right here, this negative x. Will it reflect it over the x-axis or over the y-axis?
Y.
It is y. This is a y-axis reflection. And let me actually do something to help you think about why that's the case. This example right here that we had ended up taking something that normally would have been positive and makes it negative, right? Well, normally positive is above the x-axis, and now it is below the x-axis. So when you put a negative out in front of something, it flips it down. But when you put the negative inside of things, it flips it across the y-axis, flips it left and right. So we have a y-axis reflection. It's going to flip it around the y-axis, and it's going to shift it up 1. So thinking about my graph, I think it was Will that I heard over here that talked about the y-intercept. If we take the whole graph and we shift it up 1, the y-intercept gets shifted up 1 as well. Does that make sense to everyone? Not only that, but so does my horizontal asymptote. So my horizontal asymptote is previously along the x-axis, and now it's going to be shifted up 1. So here's my horizontal asymptote. So this is at y equals 1. And then my y-intercept will also shift up 1 to be right here. So this is, not that you necessarily have to label it, but just for what we're doing right now, this is now the y-intercept of 0, 2. I think it's going to ask us for it. Yeah, right here. We can even write it in. And my horizontal asymptote is y equal 1. So this is my graph so far. Now normally, this is a 3. So it should look like this graph, right? But if I flip it around the y-axis, it's going to change, and it's going to end up looking like the second graph. That's what a rotate or a flip or reflection around the y-axis does, is it rotates the image around that line. So this is the graph roughly that I end up with. Now, because I shifted things up and down, in this case up, it does affect something. Does it affect the domain, or does it affect the range when I shift it up? The range, because the range is my y values, right? So my domain is the same. I can go far to the left, I can go far to the right. That doesn't change. But on my range, I took everything and I moved it up 1. So instead of being able to be from 0 to infinity, now I have to be from 1 to infinity because I shifted everything up. Any questions so far? Okay, same song, second verse. New equation. Let's talk about how it shifts things. So we'll start with the value at the end, the -4. What does that do?
Down.
Yeah, you guys got it now. This one would be down 4. Okay, I've got a -1 on the inside. What does that do? Right 1. Okay, so if I'm moving everything down 4, that includes the horizontal asymptote, right? So now it needs to be down here at -4, because that's what we would do if we shifted it down 4. So my horizontal asymptote is at y equal -4. Now, normally, I would just go 1 above that. Let me get these marked out so it's easier to see. And my y-intercept would be right here, right? But I'm also shifting things left and right, specifically right. I'm moving them right by 1. So that yellow dot that I just plotted, it won't be there. It will be over here. Right? The y-intercept shifted. Now, unfortunately, that means I'm going to have to do a little more work to find what the y-intercept is on this problem, because it's not going to be easy to see like the last one was. But that's where my point is. Now, this graph has that same 3 here in the front. There's no reflection, which means it's going to look again like that very first one because the value is bigger than 1. It's going to look like the first graph on the screen. The only reason this one didn't was because I had a reflection, and I don't have a reflection here. So my graph will look something like this. Okay, let's do domain and range. We'll come back to the y-intercept because that's the hardest part of this one. Okay, what is my domain? Cole's like it's obvious. What is it, Cole?
It's the negative infinity.
Yeah, it's the negative infinity to infinity. Didn't get changed at all. That shift right and left doesn't affect my domain at all. However, the shift down will affect my range. What's my range?
-4 to infinity.
Yeah, it's -4 to infinity now. All right, my y-intercept is when x is equal to 0, so we're going to have to find that now. So let's actually come back down here and do that. So I have, 3 times 0, 3 raised to the 0 minus 1, and then minus my 4. All right, so this is 3 raised to the -1 minus 4. What is 3 to the -1?
-4 1/3.
Close. It's just 1/3. Okay, the negative flips the fraction. This fraction is 3 over 1, or you can think that the negative puts the 3 in the denominator. So this is 3 to the 1 in the denominator. That's 1/3. Now I have 1/3 minus 4. If you want to get common denominators, you can. If you want to do this as mixed numbers, you can. If you get a common denominator, you'd need this as 3 over 3, right? So you'd get 1 minus 12, which is -11 over 3. If you do it as a mixed number and you think about, well, I really like 1/3 minus 4, that's like 3 2/3. So if you're doing it from that perspective and that makes more sense to you, 3 2/3 is fine as well. Regardless, my y-intercept is now x equals 0 and y equals one of these two values. It doesn't matter which one, they're equivalent. I'm going to use the -11/3, but you could use the other one. Okay, we're shifting gears. No more graphing. All right. So let's actually talk about how we go about solving exponential equations. So there aren't directions written on this slide. There should be. They should say solve. So we're going to solve these equations now. So in order to solve exponential equations, the most basic way to do so is to get them to both say whatever the base is, so in this case 2 to a power and 2 to a power. You're trying to get the bases to match, and then we can compare the exponents. So this is our goal, is to get them to have the same base on each side so that they match. You'll notice on this particular one that they're both negative, right? It's -2 to the x and it's -1/2. So the first thing I'm actually really going to do is just to divide everything by negative. So now it's already better because there's less going on. I have 2 to the x and I have 1/2. Now the left-hand side already mirrors the form that I'm looking for. It's 2 to the x. So that's good. What I want is I want to rewrite the right-hand side so that it is 2 to some power. How can I rewrite 1/2 as 2 to a power? Yeah, it's a -1. It's basically the same thing we had happen down here at the bottom with my 3 to the -1. 3 to the -1 puts the 3 in the denominator with a power that's +1. Well, I can flip it and do the opposite. I can put it back up in the numerator if I wish and just make the exponent negative. It's actually in the form that I'm looking for now. Now, while it is not true that the 2's cancel, you can, in fact, ignore them. because they match. So the only way this equation is now true is if the exponents also match. So I'm going to ignore the bases since they match, and I'm going to set the exponents equal to one another. And at that point, on this one, I'm done. This is my solution. X is equal to -1. Yeah.
I'm confused. So I see the format on the bottom.
Yes.
It doesn't. So the answer isn't what the format looks like.
This is the goal of how to get it to look so that we can actually take the two pieces and set them equal.
Oh.
That's what we're wanting. We're wanting the bases to match so that we can ignore them.
Oh, okay.
That's really what we want. We want to get the bases to match so that we can ignore them. Now, on number 6, you might have looked at that and said, okay, well, I see why you chose a 2. Both of them had a 2 in them. But on number 7, they don't both have a 2 in them, right? I mean, they just don't. However, the right-hand side being 2 has no ability to break down or simplify or change. So I do still need to use a base of 2 on this. I just have to think about what I do to the number 8 so that it also can be written as a base of 2. The right-hand side is 2 to the 1, by the way. What is 8 in terms of the number 2? How can I break it down? Yeah, it's 2 times 2 times 2, or 2 to the 3rd. So that 8 is the same as 2 cubed. So I replace the 8 with its factored form 2 cubed. So we are going to do a little factoring on these particular ones, and they don't always have bases of 2. I just have 2 examples that do here. So then properties of exponents say that I multiply these two exponents together. So this is 2 to the 3x equals 2 to the 1. The bases match, so I can ignore them. And now I can focus on the exponents. Now at this point on this one, I'm not done. I was in the last one. I just had x equals. Well, I don't. I need to solve it still for x, so what would my last step be?
Divide.
Yeah, divide by 3. So the solution would be x equals 1/3. And if you can imagine evaluating this in here, right, you can even use your calculator if you want. 8, raise it to the power of 1/3. Press enter. Make sure your 1/3's in parentheses if your calculator is getting persnickety about that. You'll get back the number 2. Now, the title of this section said exponential functions and applications, right? So we're going to focus our attention on applications for the remainder of this section. There's a very common application used for exponentials, and I know you've seen it before because it usually shows up somewhere at the middle to end of Algebra 2 in high school. It's compound interest. I want you to make a note that I'm fairly certain that your book uses a slightly different formula than this one. And while I don't normally deviate from the book, I do on this because this is the formula that's far more common and far more likely that you've seen before. So if you're looking in the book and you're like, wait a minute, this isn't what she did in class, I do know that. I'm still going to do it this way. This talks about compound interest. This is the way your banks work. You get interest upon interest by leaving your money there. It's also the way loans work. You pay interest on the remaining balance each time. All right? Let me just talk about, and I'll go down this list, what each of these values are. P is the principal. It's the amount that you either loan, right? Think of like a car loan, a school loan, a house loan, whatever. It's the amount you borrow. Or it's the amount you invest that you put in or save. Okay, it just depends on which side of the equation you're thinking about this from, borrowing or lending. T is the length of the time of the investment or the loan. It's always in years. So sometimes we don't see that given in a problem or even in real life. Somebody will say it's for 18 months. that's fine. You just have to turn that into years before you can actually use the formula to find anything about it, okay? So 18 months would be 1.5 or 1.5 years. R is your interest rate as a decimal, not a percent. So if you have a 5% interest rate, the first thing you have to do with that 5% is turn it into a decimal, 0.05, to use it in this equation. N is the number of times your interest is compounded in a year. So there are some common ones that you've heard. So if it's annually, it means one time a year. If you hear biannually, it means 2 times a year. If you hear quarterly, quarter like 4 quarters in a dollar, means 4 times a year. Monthly would be 12 times a year. And you can get more specific. I mean, those are the ones that you see used in financial institutions most frequently. But in terms of a book creating problems, if it says daily, it's 365 days a year. We're ignoring leap year, okay? If it says weekly, that's 52 times a year. So those are some other options of things that can show up. A is simply the amount you have or that you've paid, depending on your perspective, after T years is over. So after that 5 years, how much is now in the bank? After that 5 years, how much have you now paid on your car or whatever? There's one additional equation. It's not used in lending, so this is a terrible application to money, but we use it anyway. I don't really know the why, but it's used in applications that make much more sense in biology and so forth. And it's continuously compounded interest. Now, we don't continuously compound interest in the financial world. So just for the sake of our problems, we're going to look at it, but we don't really do it this way in the real world. Continuously compounded, you'll notice many of those letters are the same. I know my problem 8's showing up. Ignore that for the moment. The P is still the principal. The R is still the rate. This T is still time and years. All that's the same. A is still the amount you have after all that's gone on. E is a numerical value. It is stored in your calculator. Please use the E in your calculator. Okay, it's kind of like pi. It's an irrational number. Right? You know that pi is approximately 3.14, but you don't use 3.14 when you calculate with it. You use the pi in the calculator because it uses lots more accuracy because it uses lots more decimal places. The same is true for E. E is approximately 2.718. But you're going to use the E that's in the calculator because it's got far more decimal places of accuracy that it will use. All right, so we're going to do an example now. Our example is that we're going to invest $80,000. It's going to be at a 4% annual rate, and it's going to be for 20 years. So all of these numbers are really important. It's also important that they do give it to us in years. It is 20 years. The annual percentage rate, that right there, does not tell you that it's doing it annually. It's just telling you what the rate is as an annual rate. You might be familiar if you think about it from the perspective, you hear at least all the time when they advertise those APR. Have you heard APR? Talk about APR financing, right? Annual percentage rate, that's what they're talking about. All the rates we're working with are going to be in annual percentage rates. Okay, so we have 3 values that we need information for, or that we have information for, and then our different questions are going to be based on how frequently that we compound. The first one is annually. We talked about before, this number of frequencies affects the n. Annually means n equal 1. What did we say quarterly meant? Yeah, n equal 4. I've got a couple more on this slide over here. Monthly means n equal 12. And daily means n equals 365. It's always within a year. How many of them are there in a year? 365. The continuously, there's no n. It means we use the other equation. I didn't write that right. A equals P, e to the RT. We don't have an n. Now, on every problem, all the pieces at the beginning remain the same. The 80,000, the 4%, and the 20 years. All that's the same for every piece of this problem. So we have A equals, the p-value is the 80,000 times 1 plus. Now, my R value is 4%. But what is 4% as a decimal? 0.04. So R is going to go into my equation as 0.04. I said n is equal to 1. And my exponent is going to be n times t. So n is 1 and t is 20. Now, a word of caution one more time about using your calculator, which you definitely need to do these problems. There's no question at this point. You have to have it. I would be very careful on your exponent to just multiply the exponent out to enter it. This exponent is 20, and I would just enter it as 20. If you allow your calculator to do the multiplication on the ones that it would have multiplication to do, you run the risk that your calculator, again, does not understand what you meant by your order of operations. Maybe it will do it right, and maybe it will not. The version of the calculator that I have will not do it right if I don't pay particular attention to the parentheses. So, you're going to grab your calculator. You have to show me this, the original setup. After that, your calculator can find the calculation for you. Let me just make sort of some cautionary things. If the number ends up being extremely, extremely large, you probably made an error, right? If your 80,000 after 20 years becomes 48 million, that's not right. $80,000 does not grow to 48 million. It doesn't work like that, okay? So typically speaking, double is sort of your kind of demarcation, right? Like $80,000 in 20 years, maybe it would double. You know, if it just sat there and it didn't do anything. So kind of keep that in mind. My answer probably is going to be somewhere around 160,000, give or take. Okay, and it depends on how long it lasts for. If the length of the loan is really short, it's going to be far less than that. If the length of the loan is like 50 years, it's going to be more. But you should not be getting a number in the millions for this problem. Okay, did anybody get a solution when they plugged it in? Anybody done that yet? Will's going to try it for us. Make sure you put a $sign on there. We'll say that right now. And this is money, so we're going to have 2 decimal places because that's what makes sense.
I got like 175,300. That's rounding it up a lot, though.
Yeah, a little. So if we write it with the decimals, it'd be 289.85.
Yeah.
That sound right? Yeah. Yeah, it's 175,000. So is that in the right neighborhood? Yeah, it's about double the 80,000, right? So that seems like a reasonable kind of a solution. I mean, adjusting and thinking about whether something's reasonable or not is a good thing to do on these particular problems because parenthesis errors can happen. So yeah, it's about $175,000. Quarterly will look the same. I mean, almost the exact same equation. We have our 80,000. We have our 1 plus, our 0.04, but the n value is 4. So I've got it divided by 4 here, and I've got 4 times 20 as my exponent. So again, when I put this in the calculator, I would put this just in as 80. Now, given everything else staying the same, do you expect that more compoundings will give you more money, less money, or the same amount of money? More. And it's not going to be significantly more, but it is going to be more. So on this one, we actually get 177,337.22. It's a couple grand more, simply because it was compounded quarterly instead of annually. Okay, so the monthly and the daily work exactly the same way. We will simply change our n value. So I have 80,000 1 plus 0.04, but it's divided by 12, raised to the 12 times 20. 12 times 20 is 240. That's how I would enter it. On the daily, the same thing. We'd have 80,000. 1 plus 0.04, but it's divided by 365, raised to the 365 times my 20. I don't have that one written down. 730. I think that makes it a 730 as a value on top, I think. On the monthly, I end up getting 177,806.57. So hardly any different than the quarterly, right? Annually to quarterly changed it a lot, but that one didn't change it much. If you do it daily, it changes it a little bit more. I get 178,035.47. I wanted to make sure that we talked real quick about continuously. The formula is different, obviously. I have my 80,000. I have my E. There's no N. My R is the decimal point 0.04. And my time is still the 20 years. So the equation looks a little different. I would again put this value in and find out what it should be. 0.04 times 20, what is that? And I think it's 0.8. Is that right? Can somebody check me for me real quick? Is that right? Okay, good. So that's what I would use. I would use your E in the calculator, right? And this is going to give you more than all the other answers. Not significantly more than that daily one, but it is going to be more because continuously means all the time. So it ends up being $178,043.27. All right, awareness factor. You've got 2 homework assignments, 3.5 and 4.1, and we have a quiz next time. All right, the quiz next time is 3.4 through 4.1, the last 3 sections of material. They should be very fresh in your mind since you're doing 2 of them right now anyway. Have a great week, guys.